Welcome back to The Explainer. Today, we are cracking open something that honestly looks a lot like magic from the outside, but as you'll see, it's actually built on incredibly elegant logic. We're looking at miniChat, which is step 5 in the fantastic mini LLM series. If you've been following along with the evolution of these minimal language models with us, you know things are about to get really exciting. So grab your focus, because we are going to completely demystify how AI actually learns to talk back to you. So here's the core mystery we're solving today. Think back a bit. How exactly did we bridge the gap between a basic text generator, like the original GPT-3, which basically just guessed the next word in a vacuum, and a highly interactive chatbot like InstructGPT or ChatGPT? What was that secret ingredient that turned a glorified autocomplete into an actually helpful assistant? Okay, let's dive into this. Here's our roadmap for today. First, from text to chat. Second, supervised fine-tuning explained. Third, the magic of loss masking. Fourth, inside the miniChat repo. And finally, number 5, training and results. Section 1, from text to chat, comparing models. The mini LLM series is absolutely brilliant because it introduces just one new idea at a time. And the one new idea here should actually be a huge relief to you. The underlying architecture between Step 4's miniGPT and Step 5's miniChat is completely identical. Seriously, you don't need to learn a bunch of complex new neural network math today. Instead, we are looking at a fundamental shift in behavior. miniGPT generated text just by continuing whatever sequence you gave it. miniChat, however, is trained to actually respond to specific questions. The secret isn't in some brand new kind of brain. It's entirely in how we grade that brain's test. Section 2. Supervised fine-tuning explained. How models learn to chat. Now, what's really interesting about this slide is that this simple definition is exactly how OpenAI built InstructGPT from their base models. It's called supervised fine-tuning, or SFT. Think about how massive that shift was for the AI industry. It's the exact same base model, the exact same architecture, but instead of just throwing random internet text at it and crossing your fingers that it learns context, you train it on highly structured prompt and response pairs. And the key here, the absolute secret sauce, is that the loss, which is the error the model uses to correct itself, is computed strictly on the response tokens. Let's break down how to actually do this. We format our data as a flat token sequence that represents a single conversation turn. First, we add a specific tag, the human token. Second, we drop in the actual question or context. Third, we add an AI token. And fourth, we provide the correct response. Now, the model processes this entire string. It sees the full context of what the human asked. But, and this is absolutely vital, that AI token acts as a definitive trigger. It essentially tells the model, okay, it is now your turn to speak. The model only updates its internal weights to get better at predicting the words that come after that AI trigger. Section 3, the magic of loss masking, ignoring the prompt. So the crucial point is, how do we mechanically force the model to only care about its replies? Well, the answer is loss masking. It's honestly just like a teacher grading a student's test. Picture a test paper. It has printed questions on it and the student's handwritten answers. When the teacher grades that test, they only mark the student's handwritten answers right or wrong, right? They don't grade the printed questions. The printed questions are just there for context. Loss masking tells the AI's backpropagation algorithm to effectively ignore the human's prompt when calculating errors and only penalize or reward the AI based on the words it generated in the response section. Visualizing this makes it immediately clear. Check out the blue blocks representing the prompt tokens for a training example. In these blue areas, there is zero gradient flowing backwards. The model is simply reading, absorbing the context, but it's not actively adjusting its core weights based on these words. On the flip side, the orange blocks represent the AI response tokens. This is where the gradient flows. This is where the model is actively tweaking its parameters, deeply learning how to formulate the absolute perfect answer to that blue context it just read. Section 4. Inside the miniChat repo, practical application. What makes this whole explainer series so powerful is that it's always grounded in real, runnable code. The miniChat repository applies this loss masking theory to a specific, highly practical dataset, science Q&A pairs. So instead of trying to predict the next word of a Shakespeare play or some random Wikipedia article, this specific build is aggressively fine-tuning its weights to answer complex science questions accurately. It is fully leveraging that human and AI token structure we just talked about. And this brilliantly illustrates how minimal the setup really needs to be. Looking at the configuration table, the embedding dimension stays at 64, exactly like miniGPT.
We've got 4 attention heads, but notice the max length parameter. It has been explicitly bumped up to 128. Why? Well, because we need a longer sequence window to fit both the human's full question and the AI's complete answer within a single forward pass. It's a really small tweak, but practically speaking, it's what gives our chatbot enough memory to actually hold a coherent conversation turn.
Section 5. Training and results. Fast CPU training.
Get ready for this. 3 to 6. That is literally how many minutes it takes to train this model on a standard CPU. We're not talking days, we're not talking weeks on some massive server farm. 3 to 6 minutes on a regular computer. And hey, if you have a GPU, it takes under a minute. This is incredibly empowering. It means the fundamental mechanics of conversational AI, the exact same mechanics driving those massive bots we use every single day, can be compiled and run while you go grab a cup of coffee.
Let's move to and see how this builds out when your 3 to 6 minutes are up. The repo spits out your deliverables. You get your best model checkpoint, miniChat best.pt, which is where it achieved the lowest validation perplexity. It also generates an attention map and training curves. Now, what's absolutely crucial to understand about those training curves is that the perplexity, which is essentially a measure of how confused the model is computed strictly on the AI response tokens. Because we're ignoring the prompt tokens using our loss mask, we get a much more honest metric of how well the AI is actually performing its job of answering.
So we've seen today that simply masking the loss, literally just changing how we grade the model, completely transformed a text guesser into an instruction follower. It's a single, elegant idea with massive implications. But it leaves us with a really exciting thought. If such a small architectural trick achieved all this, what happens when we actually do change the architecture? Step 6 in the series introduces many cross-attention to align source and target data. I absolutely cannot wait to unpack that with you in our next explainer. Until then, keep learning and stay focused.